because the thing we just did kind of talks through a lot of these slides here. Sine of theta is supposed to be opposite over hypotenuse. But we've learned since that when you're drawing a triangle like this, your opposite value is really your y value. And your hypotenuse is really just your radius. But if this is a unit circle, basically your sine is equal to whatever this y value is right here. That's what sine of theta tells you. How big is the y value based on whatever angle you're talking about. Well, here's a picture I found on the internet somewhere that I hope kind of you can interpret. What they've done here is they've said, well, here's a circle that you're going around. And as you go around the circle, all you care about is where is the y value at as you make a triangle. Wherever the y value is at, that's what happens to your graph. So here your y value is little, it's getting bigger. Here your y value is big as 1, then it starts coming back down again. Well, eventually your y value starts going into the negatives. It gets as low as -1, and it starts coming back again. That's where a sine curve, sometimes we use the term sine wave, comes from, the idea of up and down and up and down. More pictures that hopefully illustrate the same concept. Cosine is very similar to sine. I think what I'd like to do, though, can you guys grab your graphing calculators? I want to show you how similar they are by putting them on the same graph. Type in sine x for one of them, and type in cosine x for the other one. And on my window, I'm just going to rechange it. Let's go from 0 up until 2 pi. For your x scale, I actually have a different idea here. You know how when we drew our little graph there, we put it into 4 quadrants? Each of those quadrants was half of pi. So let's let our x scale be pi over 2. Because it's basically going to break your graph up into 4 quadrants now. And then last thing, let's make your x min and your y min and your y max get as high from -1 to 1. Because remember how it was a unit circle? It should not, in theory, be able to get higher than 1, because that's how big your circle is. Here is what sine looks like. And here is what cosine looks like.
You put the cosine of what? Sorry.
Oh, cosine of x.
Oh.
Like, we'd like to use theta, but we can't really use theta, so we use x. I guess your calculator actually writes, like, theta as one of the options there. So, can you guys all get a graph that looks like this? Cosine's graph basically does this shape. It starts high, goes down, goes low, and comes back up. Do you guys see how there's a very big similarity between sine and cosine? Sine starts, goes up, down, up, whereas cosine starts high and goes down, up. I have a thing that I think is funny that makes sense. This is a sine graph right here. This is a cosine graph right here. Cosine is like a sine graph that failed a grade. It is exactly shifted backwards. You guys see that? Yeah. Here's sine. Right here, sine is supposed to be in grade 2. Cosine's back here in grade 1. Or here, sine is supposed to be in grade 3. Cosine is right behind it in grade 2. They're like literally the exact same as each other, except shifted back. So if that helps you remember it, cosine is basically sine that failed a grade. Back to my notes here. More of this similar kind of concept here. Cosine is really more about the x value you get in a triangle. Because yes, it's adjacent over hypotenuse, but it's really x over r. If the radius is 1, because it's a unit circle, then it's just your x value. All we care about then is, well, how big is this x value right here? And as you draw more and more lines, the x value is going to shrink in, then it'll go negative, then it'll come back, then it'll go positive. So that's where, I don't have a picture of it, but that's where the shape came from. Does that make sense? Okay, now let's talk terminology. Do you guys remember some of these words here?
Yeah.
Did everybody here take physics except for you? Anybody else here not take physics 20 at least? Okay, so quick review. Sorry, Adrienne, I think you're the only one who hasn't had experience with this then. Okay, so let me just remind everybody else in case they don't know how it works. Any sort of wave that goes up and down, you might have done waves before. We have different properties. Amplitude is based on how tall the wave is. That's amplitude. So for sine and cosine, how tall does the graph get up to? Yeah, 1. It's the same for both. Okay. It's the same thing for how low does the graph go. Amplitude is basically height, but only of like the up and down sections individually. Period is basically how long does it take the graph to repeat itself. So like from here to right here, how far is that? Or from here to here, how far is that? Or from here to here, how far is that? Good, 2 pi, yeah. How long does it take for the circle to go all the way around? 2 pi, 360 degrees. So your period is 2 pi. Does that make sense? Your domain then refers to what x values can you have? Can you have positive angles? Can you have negative angles? Can angles be 0 even? Sure. I'm going to write it a little differently though. I'm going to write it as theta is an element of the reals, just to make a point. Because x is actually theta in this example here. Like x is your angle that you're talking about. So as you have like a circle like this, can you have an angle of 30 degrees? Sure. Can you have an angle of 5,000 degrees? Sure. Does that make sense? You can pretty much have any angle you want, but your range is very limited. Anyone want to take a stab at your range?
Go to 1.
-1 to 1. So I'm going to write it like this. And again, it's the same for both graphs. The lowest number you can get to is -1, and the highest number you can get to is +1. Right, here's where it finally starts to differ. Grab your little manipulative I just had you guys make. Where are the x-intercepts in this sine one we drew? So here's the sine graph. Where are the x-intercepts? 0,
0,
pi, 2 pi. Are those the only x-intercepts though? Okay, so we need to write them in a general format. So writing them in a general format, I'm going to say they're at 0, they're at pi, they're at 2 pi. And after a while, we might figure out the pattern. How often how are they going to show up? Every pi. So I'm going to write it like this. Plus or minus pi n times. That make sense? Not 2 pi. Every pi is the next time you get the next x-intercept. So -pi, -2 pi, 5 pi, 6 pi, 7 pi, 1,000,000 pi, 5,793 pi. All of those will be x-intercepts. Head over to your cosine one on the back side of it, which looks like this. Now where are your x-intercepts? Half of pi, 1.5 pi. Where would the next one be? 2.5 pi, 3.5 pi, 4.5 pi. So writing that out would look something like this. Your x-intercepts are at half of pi, 1.5 pi, etc. You're doing the same thing. You're adding pi over and over and over again. So it could be 5/2, and 7/2, and 11/2, and really everything that's a half number is where the cosine x-intercepts are at. This is the first big difference between the two graphs. Again, this is because the cosine graph is like a sine graph that's failed a grade. Everything is just slightly behind. It's actually behind by half of pi, technically. Does that make sense? Like every grade is a half of pi. Your y-intercept was 0 for cosine, or for sine. And do you guys remember where the y-intercept was for sine? Hang on, we better make sure I know which one this is. This is sine, by the way, and this one's cosine. Where was the y-intercept on the cosine graph? Good, 1, yep. And the last thing that I copied and pasted this format because we're going to talk about the graphs of tan, cotan, cosecant, and secant later. And some of those have asymptotes, but this graph does not have an asymptote. But tomorrow, other graphs will. So
it says 0 y intercept per side? Wouldn't it go?
Oh, I'm just telling you that's where the intercept is.
Oh, never mind.
Sorry, maybe I should write it like this. I should write it as 0, 0 maybe then. And I should write this as like 0, 1. Does that help?
Yeah.
I don't mean that there aren't any. I just mean that it's at 0. How am I doing so far? Does this work? Okay, let's take a 5-minute break. I think now's as good time as any. What I want to finish the lesson though with is the idea that just like any other graph, you can stretch it up and squish it in and move it around. That's what we're going to talk about next, is how do you move this graph around? Okay, so last thing then is we can move these graphs around, just like we learned in the first unit. So you can stretch them up and down, you can squish them in and out, you can slide them, you can flip them. I have a feeling you guys are going to be pretty good at this though. So let's just, I don't want to spend too much time on this. You can change the amplitude then of one of these graphs. What you have to do is you have to put a number in front, like say y equals 2 sine theta. That would make the graph go taller. Well, like taller up and down, right? So rather than going from 1 to 1, it would go from 2 to 2 instead. Does that make sense? So if you put a number in front, that changes your amplitude. You can also squish the graph in and out. Okay. Now you gotta remember though that like if you put the graph y equals sine of 2x, that 2 does not pull it out. The 2 actually squishes in. Yeah, does that make sense? Well, another way of looking at it is if you normally were going to have a graph that looks like this, putting a 2 there means you're actually going to get 2 of them. Because you're squishing it in, there's actually more up and downs happening. Does that make sense? Whereas if you did y equals sine of 1/2 of x, that's like taking a slinky and pulling the slinky outwards and stretching it out. So let's just do like 2 of these. I think you guys have the idea. What's the amplitude of this first graph, sine theta? Yeah, 1. What's the amplitude when you throw a 5 in front? There we go. I think you've got it. Right? Yeah, that's a good way of looking at it, right? You're just pulling it out, right? In this example, though, what you're actually doing is your slinky is actually not like that thin. It's like a wider thin slinky, that's all. When you stretch it that direction like Sean just did there, that's changing the period. What is normally the period of a graph? 2 pi. It takes 2 pi for it to go all the way around the circle. But what if you throw a 2 right here instead? What does that do to the graph? Squishes it in, so now its period is only pi. One more. What if you make it 1/3? What does that do to the graph? Good. Yeah, now that's taking the slinky and that's pulling the slinky all the way out. So it's 3 times what it used to be, so now it's 6 pi. Does that make sense? Cool. Let's move on. You could do both of them at the exact same time. Let's just do this one right here. That one's sufficiently challenging. What's the amplitude of this graph going to be? What's the period of this graph going to be? When it's 4 theta over 5. Okay, so let's talk through that. If it was a big number, like say 2 or 3 or 4, 2, 3, 4 would squish the graph in. If it was 1/2 or 1/3, it would pull it out. Well, this is 4/5. It's going to pull it out by 5 over 4. It's actually a number less than 1. So your period is going to be 5 over 4 times bigger than what it used to be. What did it used to be? 2 pi. So now your period will be 10 pi over 4, which is actually 5 pi over 2. Does that make sense? So your period, it used to be 4 over 2. It used to be 4 over 2 being 2. It used to be 2 pi. And now your period is just a little bit pulled out because of that 4/5 right there. I'm not going to bother sketching the graph. I think you guys can probably use your calculator by now. Does that make sense, though? Okay, we can also do translations. I need to make sure I'm very clear on how you use your brackets here. If I do not write any sort of bracket, it is implied that the +2 and the -1 are going up and down like this. So this means take the whole sine graph and just shift it up by 1 or 2, and the next one means shift it all down by 1. However, if there is a bracket involved, like say right here, that means moving it side to side. If you do not see a bracket, assume that it's meant to be like way afterwards and it's the up and down one. So I just found some pictures here. Let's talk through what's happening. This pink graph right here looks like it's a sine graph. What's happened to the red graph? Okay, so that means that if this one right here is f of x, this one right here is f of x plus 1. Because that's what causes the graph to go backwards by 1. Does that make sense? So if this one was supposed to be sine x, then this one right here is supposed to be sine bracket x plus 1. Because that's what moves it backwards 1. I don't know what I was going for on this graph here anymore. There's a lot of graphs in there. Clearly the point being that I guess you can move the graph all over the place. I don't know. I'm sure I had a point 3 years ago when I made the notes, but I've since forgotten. This one's maybe more clear. What's happening here? I'm moving it up and down, right? So if this one right here is, this is like, say, the sine of theta, the green one. This one looks like it's the sine of theta going up 1. This is the sine of theta going up 2, maybe? This is the sine of theta going down 1. This is the sine of theta going down 2. Where does the sine graph normally have a range from? Where is its normal up and lower limits? 1 and -1, right? Well, if you drop the whole thing down by 2, now it's going to get as high as -1 and as low as -3. Because it used to get as high as 1, but now that high of 1 is now dropped down to -1, because we went down 2. And -1 drops down to 2 to get down to -3.
Why would it go from like -1 to -3 though?
Because we subtracted 2. Right? Like normally a sine graph is from 1 to 1, but if you put a subtract 2 after it, then it pulls the whole thing down. Okay. Okay. This moves the graph by pi/6 that way. This moves the graph by pi/2 that way. You guys get the hang of this? Okay, let's find those diploma questions. Let's go to the end here. Let's just go to this. So here's an old diploma question. I had to kind of take the ABCD and kind of shove it inside there because it's a pretty big graph. Here's a picture of a graph. It's either a sine graph or a cosine graph. It looks like they made it a cosine graph because that's what all the answers involve. What is a normal cosine graph supposed to look like? Well, it's supposed to start up at 1 and then go down and up again, right? Well, clearly this graph has had a few transformations to it. One of the transformations is that it's been moved up. Does that make sense? Because it's clearly been moved up. It's also been stretched. Because from here down to here is not like from 1 to -1. Like it's been pulled up as well. Does that make sense? Another thing that I think has happened is, see this A value right here? Normally the graph is supposed to start at its highest point, but it's been slid over a little bit as well. Does that make sense? Our goal is then to figure out which one of these equations is best. Now, truth be told, if this was an actual diploma, I would just use my graphing calculator, type in all 4 equations, and whichever one looked like this would be the right answer, but that defeats my purpose today. So let's see that we can not look at these 4 answers and actually work backwards to figure out which one's most logical. Do you guys see how like this lowest point right here is a 28? Because it tells you, by the way. Okay. And this highest point right here is 112, because it tells you. That can be used to help us find our amplitude. How far is it from 112 to 28? How much was it? 84. So from highest to lowest is 84. If I cut that in half, that means my amplitude is 41. Because I'm going up 41 and I'm going down 41. 42. Thank you. Did that make sense, minus the fact that I can't do basic math in my head? Okay, so subtract the two numbers, divide them in half. That tells you that your amplitude means you're going up by 42, going down by 42, which means that all of these start with a 42. So that actually didn't help, did it? Okay, another thing we should be able to do is figure out, well, where is the middle of the graph now? Like normally, where does the middle of a cosine graph go through? 0. And clearly it's now been shifted up a lot. As I look at all the different possibilities, it either went up 28 or it went up 70.
I think it's 70.
I think it's 70 as well.
Because it's not 28.
It's clearly somewhere halfway between 80 and 60, so that would make sense that it's at 70. But here's how you can figure that out, by the way. Your highest value is 112. If you go down 42, you get 70. Or your lowest value is 28. If you go up 42, you also get to 70. Therefore, 70 is the middle of the graph. So it's not A then. That one's rolled up. The last thing we got to figure out is, normally the graph of a cosine should start at its highest point. But do you guys get what I'm saying, where it's been moved over just a little bit? Well, it's been moved over pi over 2. So to shift something that way pi over 2, yeah, you need to subtract the pi over 2, basically. There you go. Does that make sense? That being said, you could use your graphing calculator on that one, but I'd prefer if at least for this example, you didn't. Let's try another one. Here's something that you guys have done a lot before, only not with a cosine or sine graph. There is a leading coefficient missing. This a value right here, in a way, is a leading coefficient. How do you solve for leading coefficients that are missing? You have to use a point on the graph.
That's what it gave you.
I gave you a point on the graph, so let's try it. Your y value is -2. Your leading coefficient of a, we don't know. It's now cosine of theta. Theta is pi over 2 minus pi over 4 minus 4. Okay. In here, what is half of pi minus a quarter of pi? You have half of something?
And if you look at me,
I'm gonna draw a picture here. Here's a circle. You have half of something.
well, it'd be a quarter.
And then you remove a quarter, so that one's gone. You're left with a quarter. So you're left with pi over 4. Minus 4. That makes sense? Yeah. I want to focus just on this little bit right then. Cosine of pi over 4. Pi over 4 is one of the two triangles we learned about yesterday. Pi over 4 occurs in a triangle that goes 1, 1, root 2, because the angles in the corner are pi over 4. Or in degrees, they're 45s. So what is the cosine of pi over 4 then? Well, cosine is the adjacent over the hypotenuse. I don't think it actually matters which angle you pick. Either way, it's adjacent over hypotenuse. Either way, the adjacent is 1, and the hypotenuse is root 2. So kind of hopping down here, I could now say it's -2 equals a. All of this stuff right here is 1 over root 2, or minus 4.
Why do you not have to include the cosine?
Because cosine of this angle is that ratio. Does that make sense? Like this thing right here is that. It's just a number, right? It's like, I'm going to say this a lot in this unit as well. You know how when you log a number, it's just a number. Well, cosine of pi over 4 is just a number. That number is whatever 1 over root 2 is. So, last steps to get a by itself. Let's add 4 to both sides. So that means 2 equals a times 1 over root 2. Times up the root 2. A is equal to 2 root 2. This question here, as a numeric response, wanted as a decimal number. So I would actually have to go to my calculator and do like 2 times root 2 and make it 2.82. I think I wanted just a 2.8 though. That being said, I have seen them ask numeric response questions where they tell you that A is equal to like x root y, and then they ask you what is x and what is y, and then your answer would be 2 and 2. Makes sense? Does that work? Do you guys have, that's where your notes end, don't they?
Yeah.
I don't know why, but I have more questions here, so there's a few more. Sorry you don't have them. Here I tell you that you apply this transformation to that graph. So here's a regular old-fashioned sine graph. What are these transformations here going to do to the graph? What does the 2 inside do? Squish it in. It's inside the graph. See that? If there was a 2 right here, pulls it up. But the 2 on the inside takes the graph and squishes it in. So I'm just going to draw squish in twice as much. What does the minus do? Down 2. All right, then it wants to know the range. What is range about x or y? Okay, well, in that example here, y is actually written as y, so it's not theta. Well, normally a sine graph gets as high as 1 and as low as -1. But if you pull the whole thing down, then it gets as low as -3, and the 1 pulls down to -1. Does that work? Okay. Okay, and last one. I want to find the y-intercept of this graph. This is a good question because you can't really type this into your graphing calculator because you don't know what theta is, so theta has to be x in your calculator, but you also don't know what k is and you don't know what b is. So does that make sense how this is challenging because you can't actually just type it in your graphing calculator? That being said, using our math skills of algebra and our understanding of what a y-intercept is, what does a y-intercept mean? Good. It means x is 0. Or in our example, it means theta is 0. The angle is 0. So it means that I'm looking for the y-intercept. I'll just write it as y. It's equal to -3 of cosine. Okay, if this thing right here is 0, do I really need to write it anymore? So it's cosine of pi over 2. I want to focus on this again. Cosine of pi over 2. Now, pi over 3, pi over 4, and pi over 6 are all special triangles. Pi over 2 is not a special triangle. That being said, pi over 2 is something that we can use this for. We need cosine. So that's this one. Where is pi over 2? Right there. Cosine of pi over 2 is 0. Does that make sense? That's where this can help. So based on that, if this cosine of pi over 2 is also 0, the fact that it's times by -3 is kind of irrelevant. So what's left? Minus b. That's your y-intercept. Should I show that one more time from the top? This is a particularly challenging question in that you really can't guess and check your work. But if you understand like what steps I just did there, it actually is kind of easy. Y-intercept means that theta is 0. If this is 0 right here, that's all useless, so that's gone. This bit right here says, well, what is the cosine of pi over 2? You're expected to know, off the top of your head, pi over 3, pi over 6, pi over 4. You should also be able to do pi over 2 and 3 pi over 2 and anything that's like a rounded number. Pi over 2, just use your little manipulative there. Cosine of pi over 2 is just 0. So if all of this is 0, that means that all of this is 0. 3 times 0 is irrelevant. The only thing left is minus b. That's your y-intercept.
Very smart.
It is kind of clever, actually. I like that word. Okay, I'm done. Any questions? Okay, quick summary then. Quick summary. I like to end with a summary. I've now taught you 2 different things that are seemingly different, but they're actually very similar. One of the ways you can solve a question like this, sine of theta equals 1/2, is you could draw a grid like this. You could use the cast rule, and you could say, according to CAST, where is it positive? It's positive in one of these quadrants. This is where you're going to find answers. You could then use one of those special triangle type things. That's the wrong one. And you could find these angles right here. That's one way of doing it. Or another way of solving it is you now know what a sine graph looks like. Sine graphs look like this. Where is it equal to 1/2? Well, it's equal to 1/2 right here and right here. You can also use your graphing calculator to find where those answers are. Does that make sense? These two things are related. They seem different, but it's the same way of solving a question. One way is using a unit circle, and the other way is using what a graph looks like and intersecting. Again, though, one of your biggest struggles is, can you deal with all of this in radians? Because you could just go to your calculator and go inverse sine 1/2. Do it properly. 1/2. And it's going to give you some decimal number. That's not helpful, because that decimal number is probably something like pi/6. And that's what you're actually going to be asked for, is you're going to be asked to find the pi/6, not the ugly decimal number. So you can use your calculator, but you can't rely on it solely, because it won't work in all situations. Questions, comments, concerns, conundrums, complaints, curiosities, criticisms, queries? Is it good? Cool. You should now be able to do most of this assignment. Okay. Tomorrow I have one more lesson. Tomorrow's lesson we're going to talk about what the graphs of tan, cosecant, secant, and cotan look like. It's actually not a very long lesson. So that's tomorrow. And then next week, then when you guys have Monday, Tuesday, you have dedicated work days for your assignment. But you should be able to do a bunch of these questions now. So. Okay, thanks for listening.